So, I'll talk about the toolbox that we have in SoundCloud to manage our microservices. First of all, I will briefly mention myself and SoundCloud. SoundCloud is the largest online audio distribution platform, and our creators upload 12 hours of audio to our platform every minute. I'm a software developer there. I joined SoundCloud 2.5 years ago. I'm a generalist, so I've worked on various parts of the architecture, and my latest position is backend development position in core engineering team. So in the year of 2013, we started migrating towards a microservices architecture. And of course, this migration wasn't a smooth one, like every other company. We changed how we structure our engineering teams. First of all, we changed our architecture altogether. We adopted plenty of new patterns. We adopted new tools. And in this talk, I will mention some of the changes that we have been through. And those changes can be categorized in 3 main sections. As said, there are architectural patterns that we have adopted, and the tools that we adopted to keep our engineers productive, and also the monitoring infrastructure that had to change altogether. And the very first thing I will talk about is Finagle. Finagle is an open source library, open source by Twitter. It's an RPC framework. It is protocol agnostic, and we picked Finagle as our default main framework for writing our new microservices. Finagle is implemented in Scala, and mostly because of that reason, we picked Scala as our default programming language. The main thing that Finagle buys us is that it's clean abstractions. Finagle describes a server software in 3 concepts. Those are features, services, and filters. I will just briefly mention those. Features is probably known to most of you. They are objects that contain a reference to a value that is not available yet. They are a really neat way of describing asynchronous APIs. And services can be thought of functions. They receive a request and then return a feature of a response. And then we have filters. Filters are wrappers around services. They sit between a service and the client, and they are able to decorate the incoming request and the outgoing response. And when we compose a filter with a service, what we get back is another service. So it returns us a new service. And because of this nature, we are able to compose as many filters as we want with a given service. And this is actually how we usually define microservices in our code base. What we usually do is that we first list all the filters that we want to apply to a specific service, and then we give the service that we want to be applied. So what this gives us is that it allows us a way of separating business concerns from non-business concerns. Non-business concerns are like exception filter, for example, and how we like some logic around caching, some logic around monitoring, logic around HTTP headers. Those are really not related to, those are not the main business logic, but they are still required. So using filters gives us a way of separating our business logic from non-business logic. So our service implementations are a lot simpler. They are to the point, they are focused on the business functions, and hence they are easier to maintain. Another thing that Finagle gives us through this separation is that we are able to reuse those filters across most of our services. Because like more or less, most of the services, they need similar set of filters. So Finagle is the first item in our toolbox. There are a lot that can be said of Finagle, but in my opinion, the main advantage of Finagle is those clear abstractions that we can build on top of. The next thing I want to talk about is, my clicker is fighting against me. Okay, yeah, client-specific APIs. They are also known as API gateways. And in the year of 2030, when we first started switching to microservice architecture, our architecture looked like this. We had a monolithic application that we called Mothership. It had a public API layer that was embedded in this code base, and this public API layer was our interface to the outside world. All of our clients, including our own clients, our website, our iOS and Android applications, and also all the other third-party applications that are working on SoundCloud was using public API to talk to SoundCloud. And public API was our decision maker between using the mothership code base or one of the few microservices we have. So over time we had to move away from this architecture because I will mention, we had plenty of problems with that, but I will mention two of them. One is product related. We were using public API for all of our applications or clients, even if they belong to a third party or even if they are own clients. So the problem with that is public API is a one-size-fits-all solution, and it doesn't cover all of the use cases of our own clients. So we need to better address the exact needs of our own clients, so we didn't want to use public API for our own clients. And the other problem is that this public API layer was maintained by single team, and all the other clients we have, they had their own client development teams. So whenever our client development teams want to release a new feature, they have to depend on public API team to build the endpoint that they need. So this created a bottleneck in feature delivery. So we wanted to avoid this as well. So what we moved towards is client-specific APIs. In this architecture, we created an API for each of the clients we have. And the responsibilities of those client-specific APIs is basically getting the request from their client, going to the microservices land, fetching the necessary data, and then custom tailoring this data according to the exact needs of their client, and then returning the response. And another advantage that we gain through this architecture is that all of those client-specific APIs, we gave the responsibility of developing them to the client development teams. So we get rid of the dependencies between our development teams as well. Those client-specific APIs, internally we call them BFFs, standing for backend for frontends. And we have been actually public about how we migrated to BFF applications and why we did it. So nowadays, if you search for BFF pattern, there are plenty of resources available. Next thing is, let's see. I will talk about Strangler pattern. Briefly, it's a pattern that is usually used when teams want to migrate away from client legacy applications in incremental steps. So this is how it works. We have a legacy application and we have its clients. First thing to be done is to writing a Strangler application that controls the traffic between those two. And then over time, we can start porting our use cases to our new application. And as we port our use cases one by one, we can start diverting or shifting some of the traffic to the new application. So it goes on like this, and after that point, it's just a matter of iteration. As we wrote or port more use cases, we can start diverting a bigger chunk of the traffic to our new application. And sometime in the future, our new application will have all of the use cases that we need. And in that point, we can decommission the legacy code base and also the Strangler application as well. So where did we use this? In the very first 3 client-specific APIs that we had written, they were all greenfield projects. We started writing them from scratch. And as we write endpoints to those APIs, we started tweaking the clients of those APIs to start or to make use of the new endpoints that we had written. So the migration process was handled in the client. However, on the public API, we had a problem because it was already implemented. It wasn't a greenfield project, and it was using our legacy code base that we wanted to move away from. And then another problem was that public API was also used by third-party applications. So we didn't have the luxury of going to the client and handling the migration process on that level. So we followed Strangler pattern. The first thing we wrote was writing a public API Strangler, an application that controls the traffic. And then over time we started writing our microservices. And as we wrote microservices, we started shifting this traffic to our microservices. And over time we created more and more microservices. So nowadays our legacy application is getting fewer or less traffic than it used to do. But it is still on production. We haven't completely migrated away from it. But now we have a really clear picture of how we are going to decommission our legacy code base. So next thing I want to talk about is something that we call critical path. So if you look at a BFF application, there are 2 main operations that we do for every single incoming request to a BFF application. Those are, first one is, when we receive the request, no matter what this request is about, the first thing that we do is fetching the contextual data for this request. This contextual data, that what we call, is actually a bag of data that contains authentication data, which user is requesting this, and what is the user ID, and so on. Geographical location, which is also very important for our business, and also the business features that this request has access to. In the very first step, we collect this contextual data, and then we proxy the incoming request to our microservices, as well as, or together with the contextual data that we fetched on the very first step. So we are doing this because the data that we collected on the first step is fundamental for most of the microservices we have, and it is required by most of their operations. If we haven't done that, what would have happened was that the BFF application would proxy the request to a single microservice, and then it would have to manually fetch this data. But then nowadays our BFF applications, they aggregate data across multiple microservices, so this operation would have happened again and again. So we're just trying to be pragmatic here. We're trying to cut down the duplicated requests that are happening between our services. That's why we preferred this architecture. However, this comes with disadvantages as well. If we put our microservices in the center, the next thing that comes is that our BFF applications. So every transaction that's happening on SoundCloud has to go through a BFF application before landing on one of our microservices. So they are sitting between our client applications and the microservices we have. So coming back to the diagram we had before, we have plenty of BFF applications, and they all speak to the same set of microservices on the first step. And we can deduce that those microservices, they receive the 100% traffic that is coming to SoundCloud. And because of this high load of traffic that they receive, we call them our critical path. As I said, there are downsides of this approach as well. There are two main things that we need to pay great attention on critical path. The first thing is that handling failures in a graceful way, because if we start dropping requests on this layer, we may take down whole SoundCloud, including every client application. So of course it's something that we want to avoid. And because of this, we need to be really careful about how we are integrating these services. And we need to make sure that those integration points, they should be able to handle every kind of failure that may happen there. The approach that we take usually is providing default values. If any unknown error or any fatal error happens, we provide a default value for the result of this microservice operation, and then we pass it down in the contextual data. And the second thing that we need to take care is traffic bursts. Because SoundCloud's business is prone to traffic bursts. So, for example, whenever someone uploads a really viral content on SoundCloud, everyone tweets about it, and this creates a huge spike of incoming traffic. And the very first place this spike slams is our microservices on the critical path. So we need to over-provision them. We need to be ready for this unexpected incoming traffic spikes. And also we are really diligent on their on-call rotation. If any incidents happen on any of those services, we are resolving them as quickly as possible. So as said, critical path is coming with its downsides, but it also reduces the cost of serving a single incoming request. So it is an item that we have in our toolbox. So the next thing I want to talk about is something that we call service layering. When our architecture looked like this, the decision-making process that we had in public API was simple. It was either using mothership code base or one of the few microservices that we had. Nowadays, we have more microservices, and the more microservices we had, the more granular their responses became. So nowadays, a BFF application doesn't just proxy an incoming request to a single microservice. They have to aggregate data over multiple microservices. So at the time, the most convenient place to write this aggregation logic was the BFF application itself. However, the next problem that we came across was that another BFF application showed up. It had a pretty similar aggregation logic. It was talking to the same set of microservices. So this duplication logic ended up being duplicated over multiple BFF applications. So in a microservice architecture, of course, like it is inevitable to have some kind of code duplication. But for some use cases, this aggregation logic was rather complex to be duplicated over multiple places. So we wanted to abstract it away. What we did was writing more microservices. So we created microservices that are responsible of aggregating other microservices. And this worked fine for a while. However, as we started writing more of those aggregator services, we ended up having more and more complicated dependencies between the services that we have. So day by day, our architecture was getting closer to this. Of course, we wanted to avoid that as well. What we came up was layers for our services. So we defined layers, and for each layer we defined high-level objectives for the services that live in that layer. At the very bottom layer, we came up something that we call foundation layer. And the high-level objective for the services on this layer is that, first of all, they don't talk to each other. They don't talk to anyone except their data storage. They have none or as less business logic as possible. They only provide simple CRUD interface for the business entities that they represent. Examples are tracks, images, playlists, users, and so on. So they only provide an interface that allows developers to create, delete, update, and read the resource. On top of it, we defined a layer called value-added layer. The vast majority of our services, they live in this layer. And in this layer, we implement the meat of the business logic. The services on this layer, they are responsible for fetching the entities from foundation layer, and then they perform their business operations on these entities. And they are also responsible, also on this layer, we still have those aggregator microservices, so we still allow talking to each other with the peer services on this layer. And then at the very top, we have our BFF applications, and they live in a layer that we call edge layer. And BFF applications are responsible for fetching data from the services that lives in the value-added layer. So this doesn't completely solve the problem of having too many dependencies or complicated dependencies. But at least it is giving us a guideline of thinking. Like whenever we are making design decisions, we can picture this framework in our minds and say that we can have a clear idea of what should be the responsibility of each service, as long as we keep this structure in mind. In this architecture, we still have the mothership code base around, and it doesn't exactly fit anywhere, but this is okay because we have a plan of decommissioning this code base. So, the next thing I want to talk about is humane registry. As I had shown before, the number of microservices we had has grown a lot. And over time, we started having organizational problems. Like at the initial times when we had 10 to 20 microservices, almost every engineer in the company, they knew about what microservices we had, how many of them they were, which teams were in maintaining them, and what operations they were supporting. But nowadays we have around 140 microservices. Our engineering team has scaled up as well. It is split across 2 continents right now. And so propagating this knowledge around the microservices that we run became an issue. Our engineering leaders, they dug up this article for us, which basically suggests building a tool that radiates this information in the organization. This article has 2 main guiding principles. I will briefly mention those principles. First of all, it says that it should be oriented around people. What does that mean is that when we think about the questions that we ask about our microservices, we usually want to know who did the latest contribution, who did the most of the contribution. That means who usually knows the overall implementation details around this code base. Who started this code base and what was the design goals, where's the engineering documentation, who wrote that documentation, who did the latest deployment, who handled the latest incident, which team is responsible for being on call and which team is maintaining the service. So all of these questions, those are the questions that we ask in our day-to-day work because we need this information and they're about people. So this tool should be answering the questions that we have about people. Second thing is that engineers are already busy enough. We don't need another tool that we have to keep up to date. So this tool has to be smart enough to find its own information. And in the article it is suggested that there are many data sources that are available in our organization that can answer those questions. Examples are our code bases, our revision control systems. So they actually answer most of the questions we have around contribution. Our deployment tool can answer the questions around deployments. Our on-call rotation schedules, our engineering documentation, our HR tools, so they can give the answers about contact details and so on. So those sources are already available. So this tool should make use of those sources instead of expecting people to keep it up to date. The last thing is that, of course, it has to present this information in a human readable way, and also it should encourage contribution as well. Even though we don't rely on people to keep it up to date, at the end of the day, like the most important information around the microservice we have, they still live in the minds of our engineers. So if they want to write this down, they should be able to do so. So this tool should also encourage contribution. So keeping those principles in mind, we implemented a tool that we call the Services Directory. It looks like this. It has a good enough UI. It goes through all of our GitHub repositories. It fetches the metadata, and it also has many integrations to our internal data sources. Live configs, our distributed tracing tool, our deployment tool, our HR tool, and engineering documentation. Those are all integrations that we implemented to this service. And even today, we are still investing in this tool because the more we invest, the more return we gain from it. This tool has been around for more than a year, and since the inception, it became the central hub for sharing the knowledge around the microservices that we run. And one of the most important points is that this tool is regularly scraping all the integrations that we have implemented to it. So if something has changed, it keeps itself up to date, so we don't have to touch it a lot. Next thing I want to talk about is Prometheus. Prometheus is our monitoring tool, and it started as a side project of two of our engineers. It was open source at some point, and now it grew out of SoundCloud. According to the last thing I heard, there are hundreds of organizations that are relying on Prometheus for their monitoring needs. When it was incepted, Prometheus had 4 main design goals, and those design goals grew out of the problems that we had with our Puris monitoring infrastructure. I will briefly go through the list. First of all, when we migrate to a microservice architecture, the number of instances that we need to monitor has grown a lot, because it used to be one single big monolithic application that we had, but now we have plenty of services running around on our production, and all of the services have plenty of instances. So we needed to scale up our monitoring infrastructure, and Prometheus helped this by having a decentralized architecture. So whenever we spin up a new cluster of microservices, what we do is we ship a monitoring service with that cluster, and that server is responsible monitoring only that cluster and nothing else. So at the moment at SoundCloud, we don't have any single set of centralized servers that tries to monitor the whole infrastructure we have. And the second thing we had is that operational simplicity. Because now our Prometheus servers are distributed across our platform, we don't have a single team that is maintaining all of our monitoring service. So we want individual development teams to take care of their monitoring needs. So they should be able to set up their monitoring service, and they should be able to operate it. But also we don't want every engineer to become a monitoring expert as well. We want this tool to be as simple as possible to be operated. And from my personal experience, I can say that Prometheus achieves this goal very well. The next thing we need was multidimensional data model, because we wanted to have a detailed view of what is going on. We wanted to have, more information out of the metrics we have, and we wanted to annotate them with different values and run queries against those values. And lastly, we needed a powerful query language to support all these operations, and we needed to have this query language should be able to allow us to write really sophisticated queries for our graphs and for our alerting rules. So I will briefly explain how Prometheus works. Prometheus expects a service to expose an endpoint that stores the stats data. And as long as this endpoint is up, Prometheus regularly scrapes this endpoint and fetches the latest stats data. And of course, Prometheus is able to do this. Getting this endpoint up to date is not a problem because Prometheus provides client libraries on various different languages. So as long as you stick to one of those, it is pretty easy to get this endpoint up and running. And of course, Prometheus is able to do this scrape operation for multiple or many instances simultaneously. I will also talk about, give an example about the multidimensional data model we have. So this is an example of a counter. And when we are defining this counter at the top, we define labels for it. And each of the label corresponds to a dimension. And when we are incrementing this counter, what we are able to do is annotating each of those dimensions with different values. This allows us, when we are querying, we are able to give different values for the dimensions that we are interested into. So one example here is that this query, it says that we are interested in all of the increments that has a status class of 5xx, and I want to see the distribution of those increments by their dimensions of service, method, and status. So this is a pretty powerful query, and we run it for almost all of our microservices we have. Again, there are a lot more to say about Prometheus, but in my opinion, the essential point is the 4 design goals that I mentioned in the beginning. The last item I have on my toolbox is that it is service level objectives. It's a project that we kicked off, and at the moment, the problem we have at SoundCloud is we have many services running on our production, and they all have different performances. Like, they have different error rates, they have different latency graphs, they have different garbage collection cycles, and so on. And the problem we are having is that we don't know what is good enough. For example, a service has a 200 milliseconds of latency. We don't know if this is good enough. We don't know if this is breaking any user experience and if it is something that we need to improve. Or we don't know if it's okay for this service to have a 200 milliseconds of latency. And this is making our lives hard when we need to prioritize work, maintenance work versus new feature development. We can of course always focus on the microservices and try to improve their performances, but we don't want to over-engineer our microservices. I mean, if the current value of a microservices performance is okay, then we should leave it like that, and we can focus on writing new cool features to our platform. But right now it is really hard to prioritize this work. So we kicked off this project in order to address this problem that we have. And in this project we defined an SLO for each of our microservices. And at the moment, SLO is defined with 2 thresholds. Those thresholds are error rate and P99 latency. What we are doing at the moment is that we are continuously keeping the track of the values for a given service. We are keeping track of error rate and the latency. And as long as a service is working or performing within the boundaries that we defined with this SLO, everything is good, and we say that this service is available and it is conforming to its SLO. However, if this service starts performing below the boundaries that we expected, then we say that this service is not conforming to its SLO and we consider it as unavailable. So we continue to keep the track of this, and at the end of the month we make a calculation. We get the ratio of how much of the time the service was working within the boundaries. We compare it to the total duration, and this gives us a value, and that value is called availability score. And this value is compared to the availability target that we defined for this service. As long as this score meets the target that we defined for it, everything is good and dandy. But then, if a service is constantly dropping below its target, then it gives us a hint. It says that, okay, maybe it is now time for us to prioritize more performance maintenance work on this microservice. And we publish this, the comparisons of each of our microservices, and it is available to all of our organization. And of course, the tool that we use to spread this knowledge is, again, services directory. So nowadays, if you go to services directory, and any engineer in our company can see how our services are performing. So I explained how we measure the availability of our services in a unified way and how we keep track of it. But the thing that I haven't mentioned yet is that how are we coming up with those thresholds? Those numbers above there, they are important, and they should be driven by product people. However, it is really hard for us to translate the expectancies of a single endpoint that lives on the BFF application to the latencies that we have on the microservices. That's why I actually couldn't mention. I can't talk about much about it because we haven't done that yet. And we have some ideas, but we don't have conclusions yet. But this is the tricky part of the problem. And I've been actually talking to a couple of people in this conference about this problem and how they are coming up with meaningful values for the error rates and the latency thresholds that they want to assign for their services. So, service level objectives, they are an important piece of our toolbox as well. And this was the last item I have in my list. I will briefly recap. So we have talked about these topics, and when I started writing, when I started putting up together some notes for this talk, I talked to a couple of my colleagues, and there had been plenty of ideas about what we can be talking about. So the list I have here is a really small fraction of what we are using at our day-to-day work. And there are plenty of other things that we can talk about. The most important being, like I already mentioned, our deployment, our CD, CI tools, how we do testing, how we are tracing the transactions that we have, and how we are doing the unit tests, integration tests. But very not, we like to be public about our work. So backstage.soundcloud.com is our technical blog, and we try to write their blog posts regularly. Also, you can follow our developers' Twitter account, SoundCloud Dev. I also added a couple of links. If you're interested, you can check it out there. There is more information available. So, actually, with that, I will close. Thank you very much all for listening. So, I think now we have time, and we can, if there are any questions on Silo, we can have a look at them. I will start from the top. How do you manage incompatible API changes between layers, if you have any? Yes, we have many. We have plenty. It is a problem. We have a couple of ways of doing this. First of all, I haven't mentioned this during the talk, but it was actually included in the original version of the presentation that I have. First of all, we have some integration states, and they are not implemented everywhere, and they are really hard to implement. But we have some of them. For the most important business features, we have those integration tests that are being run automatically. At some point, we were running those integration tests against our staging environments, but nowadays we are trying to containerize our application, and we spin up containers and run the integration tests in an isolated environment. Also, we have another method of doing manual tests. I mean, manual testing is no way a replacement for the automated tests we have, but we also have a manual testing process. We have a tool that we haven't open sourced, but this tool allows us to capture the production traffic and apply this production traffic to a target that we specified. So, and then this tool compares the responses that we get from the production environment and the responses from the target application that we have defined. And it compares those two responses. And then it is up to our engineers to investigate the result of this comparison and see if there are any unintended changes. I can follow this up in person, but these are the main topics. I will move on to the next one. What is your load balancing strategy for all microservices? Yeah, it used to be load balancers, but it caused plenty of outages. So we stopped using load balancers internally for our microservices. So first of all, we are using service discovery. Our services can be discovered, and we use DNS at the moment for this. But yeah, everything from BFF and on, like every other microservice, they discover each other using service discovery. On the very top layer, of course, we have a load balancer before our BFF applications, or in front of our BFF applications. I hope this answers. By the way, feel free to approach after the presentation for questions. I'd like to answer things in person as well. I will move on to the next one. Is a service discovery in-house made tool? Has it been open source? Yes, it's an in-house tool at the moment. Even though the framework that we are using, Finagle, it is already providing a service discovery method that is out of the box. But we implemented our own service discovery method. I wasn't in the company at the time, but yeah, I think it is. I don't know the reasons about it, but for some legacy reasons, we have our own in-house made tool. I'm not sure if that would be open source. I don't think so. I never heard any discussions about that. Okay, next one. You mentioned handling traffic bursts. Do you implement any dynamic scaling to handle spikes? That's a good question. Answer is no, we don't have it, but that's a pretty good idea. We should do it actually. But at the moment we just over-provision them, which may not be efficient, but also at the moment we are going through a migration process of how we deploy and how we scale up and down our services. So we are, at the moment we have an in-house made tool again, but we are moving towards Kubernetes. Hopefully a dynamic scheduling will be available. Okay, everything's alright. Hopefully it will be available when we did our migration. Okay, I think we have 3 more minutes, so I will move on to the next question. Isn't Node.js better than Prometheus? It has been battle tested. Prometheus has been battle tested, for sure, because we have been using it on production since I started the company actually, because I remember doing the very first Prometheus integration in our BFF application. So it has been battle tested and it has been used by many organizations, and as I mentioned earlier, the last number I heard was hundreds of organizations are relying on Prometheus. I hope I'm not lying, but that should be correct, that's what I heard. But yeah, it gained a lot of popularity actually, and nowadays there's a big open source community behind it. So isn't Node.js better than Prometheus? I cannot say. I have experience with working with Prometheus and I like it a lot, and all of the engineers, like if there is one tool that we don't complain about in our architecture, it's probably Prometheus. So yeah, it's pretty good, and yeah, comparison to Node.js, yeah, I cannot comment on that. But feel free to approach in person after the talk, so I can just give you some hints and put you in contact with other people as well. So do you use any API management layer such as Kong? I'm not familiar with Kong, but we don't have an API management layer, and I'm not sure if this question is about around documenting the endpoints we have and this kind of stuff, but we don't have such a tool at the moment. So our APIs are basically our BFF applications, and yeah, we haven't done a lot of documentation for the endpoints that we have on BFF applications. This is something that we want to change in the near future. I hope this answers. Feel free to come by in person. 1 more minute, so next question is, you have a lot of internal tools. What's the reason behind? For example, why not use, for example, Swagger instead of services discovery, services directory? Feels like reinventing the wheel. Yeah, that could be a valid criticism. We haven't used Swagger. We considered it. Actually, for the BFF applications, we are considering it. But yeah, it is the decision up to the teams that own the BFF applications. So they own and maintain their BFF applications, and it is up to them how they want to document their endpoints. But then services discovery is doing a lot of other things as well. It has plenty of integrations to, as said, our on-call schedules, our monitoring tools, and our live configs. So I feel like services directory is doing a lot more than what Finnegal would give us, what Swagger would give us. Okay, last question. I will take the next one. How do you make sure that your API gateways doesn't implement business logic? That's a good one because they actually do, and we are trying to we are trying to not do that, but sometimes it's not possible because we are trying to move fast as well. If you need to implement a feature as quick as possible, sometimes we just cheat and implement some of the logic to BFF application, and that is technical debt. So we are trying to move all of the business logic we have on BFF applications to their own microservices. This is still work in progress, and I ran out of time. For the rest of the questions, feel free to approach, and thank you very much.